We're going to talk about the subtraction of integers. In previous lessons, we've already talked about subtraction of whole numbers. So this is going to follow suit so that we add rules for subtracting integers. Let's talk about the subtraction of integers. One of the most common and traditional approaches of teaching the subtraction of integers is by teaching the method of adding the opposite. Some teachers will refer to this as adding the opposite. Some people call it keep, change, change. This is a very good traditional approach to teach the subtraction of integers. So I've got an example here where I'm going to take -3 and I'm subtracting 12. I've highlighted the -3 in red because we're going to keep that sign of that first number. We change the subtraction sign to addition and change the sign of the second number. Students that are learning this will often be used to the teacher repeating it, keep, change, change, keep, change, change. So it teaches them how to change their signs. After you keep, change, change, you go back and use your rules of addition to simplify. So if I have -3 minus 12, it becomes -3 plus -12. So this also gives students a chance to review those rules for the addition of integers. When I'm adding two negatives, I simply add them and I keep the same sign. So my answer would be -15. There are several subtraction of integers algorithms that we want to talk about. 5 in particular. We want to talk about the chip model, the number line model, the pattern model, the missing add-in model, and the charge field model. A lot of teachers will focus on the traditional approach, but I want to introduce these integer algorithms to you because some students may need a different approach for subtraction, that it may click with them better according to their learning style. Some of these are very similar to that of the addition algorithms. However, subtraction is a little bit tougher for students to grasp when we're talking about using things like the chip model. Again, just for a refresher, the chip model is a visual representation of the subtraction of integers. Or again, we're going to use colored chips to represent integers. In this scenario, I'm using yellow chips to represent a positive integer and red chips to represent a negative integer. We're again going to remind students that an equal amounts of our red and yellow chips cancel each other out, and that's a way of making 0, and that gives us a way of rewriting some numbers. So we're going to start with this example. We want to model the problem by drawing chips. I want to take -8 and I want to subtract -2. Let's see how we would do that using the chip model. First of all, I need to be able to represent my 8 red chips, and that's what I'm doing in this first line right here. I'm representing my 8 red chips. I have to take 2 negative chips away. So in my second line, I am taking 2 negative chips away. And when I do that, it gives me a remainder of 6 red chips. So my answer would be -6. This is also a good time to pull out your manipulatives. Let students use chips to actually represent the negative chips, the negative numbers, and positive numbers, so that they could visually manipulate and work with their hands. An example like this. Let's do another example with the chip model. This time, I want to take and work the problem 4 minus 7. This is one where students will need to grasp that fact about being able to make zeros and rewriting the number 4 in a different way. The problem is, I start off with +4, so I have 4 positive chips. But I need to take away 7 chips, and I don't have 7 chips to take away. So what I'm going to do is I'm going to represent 4 by using a combination of positive and negative numbers in such a way that my answer still represents 4. So I've got to take 7 chips away. So I have to make sure that I have to have at least 7 chips to take away. But it's got to represent the number 4. So this is why I have to add 3 negative chips. And I've put these in boxes to show you that these represent 0 and they cancel out. So these would actually all cancel out, and I'm still left with positive 4 chips. But by rewriting it with the chips in this way, now I can take away 7 chips. 1, 2, 3, 4, 5, 6, 7. Now that I've taken 7 chips away, you can see that I am left with 3 negatives. So my answer for 4 minus 7 equals negative 3. These are definitely types you want to pull out the manipulatives, let the students work with them, put hands on, maybe work in groups. And also, this is going to be about making the zeros with subtraction. It tends to be a little bit more tough or a little bit tougher than that with the addition. Let's look at another example. 5 minus negative 1, where again we're going to use chips. So I'm going to take and I'm going to represent my chips using, or represent 5 using my chips. So positive 5, of course, is positive 5 yellow chips. But I have to take away a negative 1. I don't have negative 1 to it. So again, I'm going to use my chips to rewrite 5 in such a way that it allows me to have a negative to take away. So I'm going to add 0 to it. This is me adding 0, but I have now that negative chip that I need to take away. And so once I take it away, it leaves me with 1, 2, 3, 4, 5, and 6. Again, this gives students a good way to see how in the world can I start off with 5, take something away, and end up with a number greater. But again, I'm taking away a negative number, so I'm taking away a debt. So this would be, again, a time that you would maybe want to talk about money, real world examples. You have $5 in your allowance, and you did owe someone $1, but now they're taking that away and you don't owe them anymore. So how much do you really have? $6. We can also use the number line model for subtraction as well, but it is a little bit different than the addition. It's still a visual representation of the subtraction of integers. But this time, instead of starting at 0 like in the addition, we start at the start of the first number. And there are many different ways that you could use the number line model to subtract. And again, this is just one algorithm using the number line approach. You can use the number line in different ways. This particular model that I want to talk to you about, though, starts at the first number and goes in the opposite direction. So if I'm subtracting a negative number, I would actually move to the right or the positive side of the number line. If I'm subtracting a positive number, you actually move in the opposite direction toward the negative numbers. That many spaces on the number line. Let's look at an example. Say I want to take negative 6 and I want to subtract negative 1. So you start with your first number. I'm subtracting a negative. Usually with negatives, I would go to the left. When I'm subtracting, I'm going to do the opposite, which isn't that really what subtraction is about, adding the opposite? So instead of moving to the left one space, I'm going to move to the right one space, and I get an answer of negative 5. Looking at one more example, 1 minus negative 3, I'm going to start with 1. I'm subtracting a negative number. Move in the opposite direction of your negative integers, 3 spaces. 1, 2, 3. So my answer would be 4. Again, this is just one approach to the number line. There are several different ways that you could use subtraction to teach, or use the number line to teach subtraction of integers. Again, we have the pattern model, very similar to that of the model for adding integers. Again, in order to be able to really take full effect of the pattern model, your students must already have a good understanding of the subtraction of whole numbers. This uses inductive reasoning. It's building those critical thinking skills. So if we look at this, I started on the left and I'm subtracting 3 minus 2. Students should know that that is 1. I have 3 minus 3. Students should know that is 0. We can see here that I am decreasing every time as the number increases here. The pattern says that I decreased. So 3 minus 4, again, I'm going to decrease by 1 and I get negative 1. I add 1 here. 3 minus 5, decrease 1 there. 5 plus 1 is 6, decrease 1 there. And we get negative 3. I wanted to look also at the right column and look at another example that's very similar to this one, except I'm subtracting negatives. Here, we can see that I am decreasing 1 each time. And what's happening to my pattern? I'm actually increasing. So when I get down here to the example I'm trying to fill in, 3 minus negative 1, I will add 3 plus 1 and I get 4. 3 minus negative 2, I add 1 and I get 5. Students typically are going to start off filling out the whole number part and then talking through the pattern, what's happening. We see that 3 is staying the same, what's happening to the middle number, and what's happening to our answer when we subtract. And hopefully they'll establish a pattern of really what's happening when they're subtracting a positive integer and when they're subtracting a negative integer. The missing add-in model is a very important algorithm. It's really taking the algorithm of adding the opposite and making it come into play. In any textbook, you'll find that the definition of the missing add-in model says that if I have any two numbers, A and B, and I take A minus B, there exists a whole number C such that I can add to B and I'll get A. We're going to call C a number that is added to the subtrahend. The sum is the minuend, and the answer is called the missing add-in. And I know that sounds really confusing, but let's take a look at that algorithm with real numbers. Say I was taking 3 and I was subtracting negative 5. All this algorithm says is that in order to find out what that answer would be, that there is got to exist some number n, so that if I take that number n and I add to it this negative 5, I should get the answer of 3. And if we have students think about what that missing number is, what number would I add to negative 5 so that my answer is 3? We know that if I take 8 and I add to negative 5, I get 3. So 3 minus negative 5 would give me 8. This would be a good time to bring out a worksheet where students would fill out the missing add-ins and practice rewriting it. An example would be negative 4 minus 7. Look how that I've changed the minus sign to the equal. 7 stays the same. And I add into it, and I think about what number do I add to 7 so that my answer is negative 4. There exists such a number. That number is negative 11. When I take negative 11 and add to 7, I get negative 4. So negative 4 minus 7, my answer would be negative 11. The charged field model, very similar to the chip model. Again, we're using charges instead of chips. So I've tried to draw you an example of here of how we would use the charges instead of the chips. I'm going to go back and I'm going to take negative 3 and I'm going to subtract negative 5. So if you look in this first example that I have here, I've represented negative 3 with 3 negative charges. My problem is I've got to take 5 negative charges away, but I don't have that many. So I need to rewrite the number negative 3 in such a way that it still represents negative 3, but also written in a way that I have enough negative charges to take 5 away. So I'm going to rewrite negative 3 by 5 negative charges and 2 positive charges. And you can see that if I cancel these out, making that 0, that one thing that we keep talking about, I still represents -3, but I've written it in such a way that now I can take the 5 charges away. So when I subtract the 5 charges, it leaves me just with the 2 positive charges. So -3 minus -5 would give me +2. And we can check that with our keep, change. Keep this sign, change your minus to subtraction, change the sign of my 5, keep, change, follow your addition rules. The addition rules, when I'm adding a positive and negative number, is to subtract and keep the sign of the larger number. So my answer would be +2. I wanted to finish up today just talking about some helpful hints on the subtraction of integers. We've mentioned it before, very important to use manipulatives. There was an example of how you could go to a hardware store and they have these things called tile spacers, and they look like pluses, and you may have seen them before. They're little foam pluses that you put in the middle of 2 pieces of tile so that you lined it up correctly when you put the grout. But the good thing about it is you can take that plus sign, and you would have some of them that you would not manipulate, you wouldn't change them, and have your pluses, and then you take and you cut the tops and bottoms off of it and you make negatives. So you can use your charges, but then that gives students just a simple, cheap manipulative that you don't even have to order off of Amazon, and you can go and let them play with those tile spacers, the plus charges and the negatives. Practice making zeros, giving them a hands-on, have a friendly competition, maybe at your tables or at your groups. And as always, anytime that you're teaching, especially these young children, you want to make it fun. There's so many resources that are available online. There's an integer battleship that you can print out and have a friendly competition. It's building their skills, they're having fun at it, and they're going to enjoy it more. And again, I can't emphasize how important it is that we build this foundation while they're young, because the foundation that they get in early grades in math is going to dictate how well they perform in the higher grades. It is so important to have a good foundation in mathematics. And also, we mentioned this several times, use real life examples that they understand. Talk about their allowance. Talk about money examples for integers when we're talking about positive and negatives. And hopefully they're going to be able to grasp those concepts a little better. And there's so many more things out there that as you begin to teach your students, you're going to learn about new activities that you can do, how to make it more fun, how to make it interactive. And every year you just get better and better teaching.